In exercise 521, we have a number of molecules that all have more than one chiral center in them. And both of these molecules have the same pieces, the same molecular formula. They're even attached in the same way. So for example, A here, both of those molecules are 1,2-dimethyl cyclohexanes. But they're different because of their orientation in space. And in other words, they're different because each of these molecules has chiral centers, and the chiral centers have different configurations. They're different hands. So these molecules are in a sort of strange position. They're really similar because they're connected the same way, but they are technically different, and they will fit into pockets differently because of the different hands that are on them. And so we just need a precise way of navigating that relationship, a relationship between molecules that are so similar and yet are so different. So similar because of the way they're connected, so different because of how those connections are oriented in space. So to think a little more precisely about this, there's the concept of enantiomers and diastereomers. Enantiomers are compounds. The two molecules are going to be enantiomers if all the chiral centers switch configuration. So if they're all S, then the enantiomer would have them all R. If they start out as all R, then the enantiomer would have them as all the chiral centers as S. So we'll know that these two molecules are enantiomers if all of the chiral centers in the molecule switch. That's a special relationship. If some of the chiral centers switch but some don't, then the two molecules are not enantiomers. They have a different relationship, and that different relationship is given a different name. The name is diastereomers. One other note that I'll make is that another example of diastereomers are cis and trans. And maybe I should do that in purple so that you can see the continuity. Cis and trans are also diastereomers. The technical definition for these is that enantiomers are non-superimposable mirror images. You get that if all the chiral centers switch. And diastereomers are molecules that are not the same, but are also not non-superimposable mirror images. And you get that if some chiral centers switch and some don't. You also get that in the case of cis and trans. But this is what we're going to use to describe these relationships. The options are either enantiomers if all the chiral centers switch, or diastereomers if some switch and some don't. And those terms give us precision in navigating the line between being the same molecule and being different. We're trying to figure out exactly how similar these are going to be. And that depends on whether they're enantiomers, all the chiral centers switch, or diastereomers, where only some do. So it'll let us think more clearly about their three-dimensional relationship to each other. So let's get some practice doing that. Now, in order to determine that, we have to determine the handedness of all of these chiral centers. Technically, that is how you would want to show your work for this problem. So, we're going to use the techniques we learned in the videos for exercise 5.9. Now, because if I assumed you didn't know anything in those videos, the explanation for these exercises would be so long. I'm going to assume that in this video, I'm going to assume that you are able to figure out the priorities of branches. You're able to recognize chiral centers, and you're able to figure out the priorities of the branches coming off of the chiral center. So if you don't feel comfortable with that, go back to the videos for 5.9 and see how it's done there. Practice that a little more. For right now, in this first molecule, we have two chiral centers. Let's look at the top one first. I'm just going to assign the priorities quickly, so you can work these out on your own to check to see if they're correct, and using the method we learned in the videos for 5.9. The highest priority is going to be this carbon number 1. This will be number 2. This will be number 3. And there's a hydrogen here going away. That will be number 4. So that's the first step, assigning priorities based on atomic number. The second step is to make sure 4 is going away, which it is. That makes our life easier. That means we can go from 1 to 2 to 3. That's clockwise. And so this first chiral center is R. If we go through a similar procedure for our chiral center down here, the priorities here, this will be carbon number 1, 2, 3, and now we have a hydrogen coming out at us. That hydrogen will be number 4. So that's the first step, assigning priorities based on atomic number. Second step, make sure 4 is going away. Here it's not, it's coming out at us. So we're still going to go from 1 to 2 to 3, but whatever configuration we'd think we have based on that, we're going to switch. Now, going from 1 to 2 to 3, that's counterclockwise, so you'd think you'd have S, but because 4 is coming out at us, it's actually R. So this chiral center is also R. Oops. So those are the two configurations there. If we go through the same procedure on the molecule on the right, for this first one, let me draw in the hydrogens. Here the hydrogen is coming out at us. And so the priorities here will be 1, 2, 3 for the methyl group and 4 for the hydrogen. That's the first step, assigning priorities based on atomic number. And then make sure 4 is going away. Here it's not. It's coming out at us. That means we're going to switch the configuration. And you go from 1 to 2 to 3. So it's going clockwise. You'd think it would be R, but because 4 is coming out at us, it's actually S. So this is S. Now, I'm doing this very fast. If you're not able to follow along with these steps, make sure you go back to the videos for 5.9 and practice the method for getting these a little bit more before you attempt this type of problem. For this chiral center at the bottom, you would want to assign priorities. So the highest priority will be this carbon here. The second one will be this. The third one will be this. And the fourth one is the hydrogen, which is going away. So that's the first step, assigning priorities based on atomic number. Second step, make sure 4 is going away. It is. That means we can just go from 1 to 2 to 3. And because it's counterclockwise, it's S. So that chiral center is S, the left-handed version of itself. So notice, all chiral centers switched configuration. So these two are enantiomers. R went to R, R went to S, R went to S. All chiral centers switched configuration. So the relationship between these two molecules is that they are enantiomers, just like your hands or your feet. They are enantiomers. And so in the answer for this, you would want to give the configuration for each of the chiral centers, show that they switched, explain all of them switched, and so they're enantiomers. So you're showing your reasoning for these. For B, we're going to do the same thing. First, let's assign priorities. I'm going to start with this chiral center here. The priority at the bottom is 1, 2, 3. And the hydrogen is going away. That is priority 4. 4 is going away, which is good. So we're just going to go from 1 to 2 to 3. That's clockwise. So this is R. If we do follow the same process for the chiral center at the bottom, the highest priority is this carbon on the top. The second highest is here. The third highest is the methyl group. And number 4 will be a hydrogen, which is going away. So check to make sure 4 is going away. It is. So we're going to go from 1 to 2 to 3. We're going counterclockwise. So that chiral center is S. We want to do the same thing for the other molecule. Here, let me draw in the hydrogen that's coming out at us. So the priorities here, this carbon at the bottom is 1, the carbon at the left is 2, methyl carbon is 3, the hydrogen is 4. That's the first step. Second, make sure 4 is going away. It's not. It's coming out at us. That means we're still going to go from 1 to 2 to 3, but whatever configuration we'd think it would be, we'll switch it. So here, it's going clockwise, so you'd think it would be R, but because the fourth priority is coming towards us, we switch it and it's actually S. So this chiral center is going to be S. If we go through that same procedure for the bottom here, we assign priorities. This carbon on top is 1, to the left is 2, the methyl group is 3, hydrogen is going away, and that's number 4. So when you go from 1 to 2 to 3, notice 4 is going away, so we're going to keep whatever configuration we have. We go from 1 to 2 to 3, we're going counterclockwise, so the configuration here will be S. So now notice, one chiral center switched, but one didn't. If some chiral centers switch but some chiral centers don't, then the relationship between those two molecules is that they are diastereomers. Diastereomers have more in common even than enantiomers do. So these two, so you'd say some chiral centers switched configuration, but some didn't. And so these are going to be, the relationship between these is that they are diastereomers. So the new thing here is not finding the RS configurations. I'm doing that very fast here because we mastered how to do that in previous videos. But given those configurations, quickly finding those, seeing how they switch between two molecules and identifying their relationship, the closeness of those two molecules based on their arrangements in space. So here in C, we have a couple of chiral centers. Let's work on these one at a time, assign R or S handedness, the chirality to each one. This molecule on the left, the oxygen is number 1, the carbon on the right is number 2, the carbon on the left is number 3, and there's a hydrogen going away, that's number 4. Make sure 4 is going away, it is. So we can go from 1 to 2 to 3, that's clockwise, so that chiral center is R. For the chiral center on the left, assign priorities. Chlorine is number 1, the carbon on the left is number 2, the carbon on the right is number 3, and the hydrogen, which is going away, that's number 4. Make sure 4 is going away, it is. So then we just go from 1 to 2 to 3, we're going clockwise, so we'll keep this configuration, it's R. So on the molecule on the left, we have 2 right-handed chiral centers. For the molecule on the right, let's look at that left chiral center first. Oxygen has a priority of 1, carbon on the right will have 2, carbon on the left will have 3, and the hydrogen, which is going away, will have a priority of 4. Make sure 4 is going away, it is. So then go from 1 to 2 to 3. We'll keep this configuration, it's clockwise, and so that's R. So this is an R, right-handed chiral center. For the chiral center on the right, first assign priorities. Chlorine's number 1, carbon on the left is 2, carbon at the bottom is 3, and the hydrogen, which is going away, that's 4. So make sure 4 is going away, it is. So we'll keep whatever configuration we get when we go from 1 to 2 to 3. It's counterclockwise, so that's S. Okay, now we're able to tell the relationship between these. One chiral center switches, but one chiral center stays the same. So these are diastereomers. If some chiral centers ever switch, but some don't, the relationship between the molecules is diastereomers. So you would write some chiral centers switched configuration, but some didn't, and so these molecules are diastereomers. They won't fit in pockets the same way, but they have more in common than enantiomers do. This down here, we have 3 chiral centers, so let's get to work. Start at that one at the top. Assigning priorities, the oxygen's number 1, the carbon on the right is number 2, the carbon on the left is number 3, and we have a hydrogen that is going away, and that is number 4, priority 4. So second step, make sure 4 is going away, it is. So we're going to keep whatever configuration we get when we go from 1 to 2 to 3. That's clockwise, and so we get that as R. So this chiral center is the right-handed version of itself. For the priorities for this next one, the chiral center just to the right, that one is, the first priority will be this one to the left, second priority, third priority is the methyl group, and the fourth is going to be the hydrogen, which is going away. And like I said, I'm doing this very fast because we walked through how to do this in a previous video. I want to get to the part that's new here, which is relating the two molecules to each other as either enantiomers or diastereomers. But remember, a lot of things are tying here, so really when you work through this problem, if you're working through it from scratch and you're having trouble seeing what I'm doing, how I'm getting these numbers, make tables. You'd make a table for this carbon, for this carbon, for this carbon, and you'd go through the procedure that we went through for exercise 5.9. So these are our priorities. Make sure 4 is going away. It is. That means we're going to keep the configuration that we get from going from 1 to 2 to 3. We're going counterclockwise here, so that configuration is S. So that's the left-handed version of itself. Now let's take a look at this last chiral center at the bottom right. The priorities here are 1, 2, 3, and the fourth is hydrogen, which is coming out at us. Remember, in these tetrahedral molecules, you always have 2 bonds in the plane that are just regular lines, 1 bond coming out at you and 1 bond going away. So those are the priorities there. Number 4 is coming out at us, so that means we're going to have to switch whatever configuration we get when we go from 1 to 2 to 3. Now, we're going counterclockwise, so you would think it would be S, but because 4 is coming out at us, it's actually R. So that chiral center is actually R. So we have the chiral centers on one molecule. Now let's figure out the chirality of each chiral center on the molecule on the right. For this first chiral center here, we have a priority of 1, 2, 3, and the fourth thing is the hydrogen that's going away here. Now, the fourth thing is going away, so that means we're going to keep whatever configuration we get when we go from 1 to 2 to 3. That's counterclockwise, so the configuration is S. If we go to the next chiral center, this one right here, the priorities, we have 1 to the right, 2 to the bottom, 3 is the methyl group, and 4 is the hydrogen that's coming out at us. So number 4 is not going away. That means we're going to have to switch whatever configuration we get when we go from 1 to 2 to 3. That's clockwise, so you'd think it would be R, but because 4 is coming out at us, it's actually S. So that chiral center is S. For the third branch, the third chiral center here, the priorities are number 1 above, 2 to the right, 3 is the methyl group, and 4 is the hydrogen, which is going away. Now 4 here is going away, so that means that we're going to keep whatever configuration we get when we go from 1 to 2 to 3. That's clockwise, so that configuration is R. So that chiral center is a right-handed version of itself. Okay, now notice that if you number this system from the OH, the carbon that has the OH on it, down to the other methyl group, we have 1, 2, and 3. If you number the same way on the other one, so start with the OH and then go down to the next methyl group, we have 1, 2, 3 like that. The chiral center on carbon number 1 switched. So it went from being R to being S. The chiral center on carbon 2 stayed the same. It went from being S to staying S. The chiral center on carbon 3 also stayed the same. It went from being R to still being R. In other words, some chiral centers switched, the ones in green, and some chiral centers stayed the same, the ones in purple. And so the relationship between these two molecules is they are diastereomers. So because some chiral centers switched configuration, but some didn't, these two molecules are diastereomers. And that gives precision to the relationship between them. They have the same molecular formula, they're connected in space, some of their chiral centers are even the same, just some aren't. And that'll give us a better sense of how those two molecules will relate, one and the other, respectively, to the stuff that they're surrounded by. How similar and how different their relationships to those things will be. Let's say, for example, the reason, and you might say, okay, fine, why don't we just know that it's different? There's a different chiral center, so the molecule is completely different. Well, watch out. What if these were drugs? But as you'll see with drugs and with hormones and with molecules that are biologically active, it's not always the whole molecule that creates the effect. Sometimes it's just a part. So if the part of the molecule that makes the effect are these two methyl groups, well, those are the same on these two molecules. So these two molecules would both function as the drug. But if the part of the molecule that's responsible for the effect of the drug is the part that has the chiral center that's switched, well, then they'd have different effects. But notice, here there's a chance that they could have the same effect, and that chance does not exist if the two molecules are enantiomers. If all of the chiral centers switch, then there are no two pockets that would ever line up in the same way on both of the molecules, at least the parts of the molecules that have the chiral centers. Okay, one more time, let's practice with this. Notice both of these molecules are 2,3-dimethyl hexanes. So if you were to circle the backbone here, notice you have 1, 2, 3, 4, 5, 6. So the backbone is hexane. You have a methyl on carbon 3, another methyl on carbon 4. So that's 3,4-dimethylhexane. And the same thing here, the backbone is this right here. That's the longest carbon chain. 1, 2, 3, 4, 5, 6. So the backbone is hexane. You have a methyl group on 3, a methyl group on 4. Both of these molecules are 3,4-dimethylhexane. So the only difference could be the configuration of the chiral centers at carbons number 3 and 4. So let's see how that plays out. Let's start with this chiral center here. The priorities attached to that, it's going to be 1 to the left, 1 to the right, 2 to the left, 3 on top, and number 4 is going to be the hydrogen, which is going away. So because the fourth group is going away, we're going to keep whatever configuration we get when we go from 1 to 2 to 3. That's clockwise, so the configuration is R. For the next one, the other chiral center, For this one, we can apply those same rules. We're going to get priority of 1, 2, 3. The fourth thing is the hydrogen, which on this atom is coming out. And so because the fourth thing is coming out, whatever we get when we go from 1 to 2 to 3, we're going to have to switch. So going from 1 to 2 to 3, it's clockwise. You'd think it would be R, but because 4 is coming out, you switch, and it's actually S. So the chiral center on the right there is S. So let me show you how that would be represented in the name. The name for the molecule on the left, you always put the chirality, in front of the rest of the name. So remember, if we had it numbered from 1, 2, 3, 4, 5, 6, then here we would have in front of the name, in parentheses, 3R, 4S, and then the rest of the name. So that molecule on the left is 3R4S 3,4-dimethylhexane. Now, we go through the same procedure for the molecule on the right. Let's find out the handedness of each of those chiral centers. So our first chiral center, right here, assign the priorities. Priority 1, 2, 3, and 4 is the hydrogen, which is going away. Now, 4 here is going away, so we're going to keep whatever configuration we get when we go from 1 to 2 to 3. That's clockwise, and so the configuration for that chiral center is R. If we go to the other chiral center, this one right here, assigning priorities, we get 1 on the left, 2 at the bottom, 3 is the methyl group, and 4 is the hydrogen, which is coming out. So 4 is coming out at us, and so we're going to have to switch whatever configuration we get when we go from 1 to 2 to 3. It's counterclockwise, so you would think it would be S, but because 4 is coming towards us, we switch it, and it's actually R. So that chiral center is R. And so the name for this compound is not just 3,4-dimethylhexane. We're going to take that name, and in front of it, if you number this chain, so just like this one, we numbered that chain, we'll number this chain. The name for this compound is, we put in parentheses way in the front, 3R, 4R, always between numbers and letters goes a dash. So 3R, 4R, 3,4-dimethylhexane is the compound on the right. So notice, in these molecules, one of the chiral centers stayed the same, the chiral center on carbon number 3. But the other chiral center on carbon number 4 changed. So notice again, 3 stayed the same, but 4 changed. If some chiral centers keep the configuration, but some don't, some switch, then the relationship between those two molecules is that they are diastereomers. And so that's what we have here. 3R4S 3,4-dimethylhexane and 3R4R 3,4-dimethylhexane are diastereomers. So those two are diastereomers. So that's how we can get a sense of the relationship between two molecules, the closeness or the difference between two molecules based on their stereoisomerism. If all of the chiral configurations switch, then the two molecules are as different in three-dimensional space as they could possibly be. They're enantiomers. And if some of the chiral centers switch but some of them don't, they're still not the same molecule, but they're closer. And the name for that, the term for that, is they're diastereomers. And so we can describe those stereoisomeric, those three-dimensional